Now today in this lecture we are going to see both BFS and DFS, breadth first search and DFS. And this program says BFS and but this is only DFS here. DFS. Remove this one. Remove this. Delete. This is for BFS. Okay. Okay. Now what is BFS? Breadth first search. In the breadth first search, what we'll do from a given in a graph. First, we will represent that graph into adjacency matrix. We will represent that graph into adjacency matrix. Okay. Now I will take one graph. We will represent the adjacency matrix. Then we will traverse. And the same way we access all that. We will give a starting vertex, and I will check it. BFS. So what is we have here? We are going to write this program using adjacency matrix. Now suppose we have 1, 2. Okay. Shall I take? Okay, I will take a tree structure. It will be more easy. Then we'll take the simple one. Okay. Let me take a tree one. A tree like graph. Then it will be easy to understand. BFS and AFS. So 1, 2, 3. Then we have 4, 5. Okay, and 6. 4, 5, 6. Okay. Now this is also a graph. Okay. Now you can consider it as a tree also. But this is actually what we are doing is graph traversal BFS. Now what is the adjacency matrix for this? The adjacency matrix is 1, 2, 3, 4, 5, 6. So it is n by n matrix. 1, 2, 3, 4, 5, and 6. Okay. So there are no loops. So diagonal element will be 0. 1 to 1, it is 0. See this 1 to 2. We have 1 to 2 and 1 to 3. 2 to 4, 2 to 5. So whenever there is an edge, there you have to put 1. Okay. So here we have 1 to 2 edge. I'll put it as 1. 1 to 3, then 0, 0. Okay. Next, what about 2? 2 to 1, there is a edge. 2 to 2 is diagonal 0. 2 to 4 and 5. 2 to 4. 2 to 4 and 5. It is 1 here. 2 to 4 is 1. 2 to 4 and 5. 1 and 0. What about 3? 3 to 1, 3 to 6. 3 to 1 and 3 to 6. We have edges. So wherever there is an edge, I will put it as 1. What about 4? 4 to 2. We have edge. Otherwise, no edges to other thing. Okay. Then 5 to 2. 5 to 2 there is a edge. Otherwise, no edge. What about 6? 6 to 3. So 6 to 3 we have edge, and this is our input. So this is our input. What is how you traverse in DFS? In sorry, BFS. How you traverse in breadth first search? Breadth first search is what? First, suppose this is a starting vertex from where you want to start the traversal. Then you will travel both the nodes breadth wise, level wise. Then you will come here. You both. Then you come back and you visit this one. Okay. So that is what you go level wise traversing, and this will be last. Whereas in a depth first search, what we do, we come here, We don't go to 3. We come here, we come back, we go here, and we will travel all the nodes. Okay. So let me run the same program. Remember this matrix? We will give the same program to program as an input. Okay. Now how to implement this in computer? Okay. Suppose you want to implement this. What is the way? When I say BFS, BFS, we use Q, as Q is first in first out data structure. So how it is done? It is done like this. If I have a Q, and starting vertex is 1. If my start vertex is 1, from where I want to start the BFS traversal, I will insert that vertex into Q first. I will insert it to Q, then I will, so inserting Q is called NQ. I'll insert it, then I will explore. So this is called visiting the vertex first, visiting, then explore the vertex. 2 operations. Exploration of a vertex. So first thing is what? We have visited 1, that is the index from where you want to start. I will insert this into Q, then I will pop and print. No, sorry, it's not pop. I will DQ. I will DQ, that is remove, insert and remove and print 1. Print 1. But when I exploration, I will check what are its neighbors. Its neighbors are 2 and 3. I insert those into Q. Okay. And once I printed and I remove from the Q, I will take the next element, which is 2. I'll print 2. I'll explore 2. What are 2's neighbors? Where 2 is connected? 2 is connected to 1, 2 is connected to 4, and 2 is connected to 5. 2 is connected to 1, 2 is connected to 4, 2 is connected to 5. But whenever I insert those nodes into Q, I will mark them as what? Mark them as visited. So I'll make them as visited. This is visited. This is visited. This is visited now. 1, 2, 3. Okay. When I explore 2, I will check these neighbors, all neighbors. But as this is visited, I will not insert this vertex 1 into Q, but I will insert 4 and 5 into Q. Now I'll insert 4 and 5 into Q. 4 and 5. Okay. Now 2 is over. I'll remove from 2. Next, what is there in the queue? 3 is there in the queue. I'll print 3. I'll print 3. I'll check what are its neighbors. So already this is visited, 1 is visited. Only 6 is left. Okay. So I will insert 6. I insert 6, and as they are visited, we will what we'll do? We'll mark them as visited. We'll mark them as visited. Okay. Now you check the queue till the queue is empty. You have to remove all the elements and print. So 4 you remove, print it on the screen. 5 you remove, print it on the screen, and 6 you remove and print it on the screen. So this is how DFS will there. Suppose if you take some other vertex, you can take like 4. Then what will be the BFS? You print both. Initially, what you will print? Breadth first search. You will print 2, you will print 1, 5, 6, and come back and you print this 5. Okay, we learn this program. Okay, now what are you doing here? See this. This is breadth first search. Enter the number of vertices. Okay, suppose if I enter what is the number of vertices here? 1, 2, 3, 4, 5, 6. Okay, if 6 is the number of vertices, then you should enter 6. Then for now, remember, as programs, to understand it properly, I have taken C array. starting with 1, not with 0. Okay. Anyway, we have 0 available. 0 available as it is sizes of what? Array A is 20 rows, 20 columns. Okay. And hardly we will enter 5 or 6. So that's why I'm taking I equal to 1. Suppose if I enter 5, it will be 1 to 5. You can see this I less than or equal to n. I less than or equal to n. Okay. So I'm reading here. Enter the number of vertices n. For I equal to 1, I less than or equal to n, I plus plus. For j equal to 1, j less than n, I, j plus plus. Now a print message saying enter 1 if percentage d has a node with percentage d. What is the I here? I is initially 1. So what you should do? You should enter 1 if you have a edge from 1 to 2, 1 to 3, all those vertices. Okay. Otherwise you should enter else 0. Okay. Then you read all the values. After reading, what we have is the adjacency matrix. That I will print it on the screen. So this is how a graph is represented or stored in the C program using adjacency matrix. Understood? Now, how we have now what we'll do? We will try to run BFS, breadth first search, on this graph. Now, for I equal to 1, I less than or equal to n, I plus plus, I have taken one more array. As there are number of whatever the number of vertices we have, so those all I have taken array of vertices, naming the name called visit. So I have to make a flag, that the status whether a particular vertex is visited. If a particular vertex is visited, I will not visit them again. So what I am doing here, I am making I'm making all the vertices as visited equal to 0. Then I will read the input from the user saying enter the source vertex. Enter the source vertex, which is S. Okay. Then I will call breadth first search with the starting vertex, source vertex, and the number of vertices. Is the code visible to you properly, or shall I make it large? Is it visible? Okay. Okay, fine. Okay. Now you call BFS with the source node and the number of vertices. After once it is done, we will print all the information of BFS traversal. Then again, it takes a lot of time to enter input. So after entering input, suppose I am printing a message saying, do you want to continue with the same input? If you say yes, it will ask you again, what is the next vertex from where you want to search. Okay. Now this is just for the namesake dummy. Okay. What we'll do, we will read a character C while C equal to what? C equal to S. We'll come back here to the do loop, and we'll check enter the source vertex. I'll read the vertex again, and then again I will check for BFS, breadth first search. Okay. Now scanf percentage, why they have taken dummy, let me tell you later. Once otherwise what you can directly take character C, but sometimes what happens, sometimes the value will not be stored here. You have to flush the input. For that we have a command called f flush stdin, but sometimes that doesn't work. So this works here. We'll check it later. Now wide BFS, once you call here BFS with source node and the number of vertices, you come here. Now what you have to do here, first starting with the starting vertex. Now see this, S is the source vertex and N is number of vertices. Int P and I, two temporary variables. Initially the whatever the vertex we have, the starting vertex, we will add S, we will add that vertex into Q. So where is add here? Add function is down here. Add int item. So yes, we are adding if rear equal to 19. Now as they have considered 19, I can take it as an okay, Q is full. Okay, that is they have taken max value. Doesn't matter, it's okay. Okay, we can change this. This is a Q program. So we are adding into Q. It's Q full. Else what? If rear equal to -1, I am adding it. I will make initially it's rear equal to -1 up there. They are global variables. You can see this front and rear both are -1. Both are -1. So if rear is -1, initially the first item I will increment. I will increment rear, make it Q of 0, insert item. Okay, and I'll increment front plus plus also. So both front plus is now and rear both are pointing to 0 value, or in our case, okay, in our case, what is that we have? It is 1. No, we are taking array size is 1, but this is for this purpose. What? This is q. So q I am taking for matrix, I am taking from starting with 1. As far as q is considered, q I am considering from 0. Else what I will do? If it is if rear equal to 19, q is full, else I will read input rear equal to -1, q equal to this is only for first time. Otherwise, what I will do? Else q plus rear, front will be there as it is, and I'll move the q to next element after inserting. That is for that. What about delete q? For deleting, see this, if a front is greater than rear, then that means what? That means front has crossed rear, then it is empty, we cannot do it. Or front equal to -1, that is also means what? Q is empty, we cannot access element from the empty. In that case, I'll return 0. Otherwise, what I will do? Q equal to q of front plus. I'll read the element, increment front, and return k. Now, okay. So where we were here, when initially source and destination, source and number of elements come, I will insert the first vertex into q. Then I'll make that visited flag of that particular s equal to 1, that vertex equal to 1. Then what I will do? Immediately I will delete. I'll say delete. Now initially the first vertex is inserted and I have deleted it, so that will come into p. Now p not equal to 0. See this, if front is greater than rear and front is not equal to -1, front equal to -1, that means it is empty. If q is empty, I will return 0. Otherwise, I will return what? The vertex q equal to q of front plus. So when you delete it, means delete means what? Delete element from the q. That time it is copied into p. If p not equal to 0 means what? It is empty. Print %d. Otherwise, if it is not equal to 0, we have a vertex. If it is 0, p will be 0. If p not equal to 0, what we are going to do? We are printing that particular vertex p. So that is on the output. Then what I will do? While p not equal to 0, when p equal to 0, that time empty it is, we don't have to do anything. If p is not empty, that means we have a vertex. Now we have to check its neighbors. So for I equal to 1, I less than or equal to n, I plus plus. Now check the neighbors. If a of pi, that is the current vertex, okay, a is a of p. P means what? The first one, okay, p. A of pi, see how to check this one? How to check whether we have okay, we'll come back here. How to check there is a connection between 0 to 1? See, this is p, row number. P is row and column is the next vertex. Suppose I have a edge from 1 to 3, then this is p. P is what? 1, and that is p is 1. And what about I? I is 3. If 1 comma 3 is 1, that means there is a edge. Okay, now let me take this one. If p and I not equal to 0, that means it is 1, and visited of I not visited of I, that particular vertex flag here, p of I, this I and visited I, if they are if it is not visited, that means if it is 0, then we are going to add those vertices into q. So I'll say add I, then make that vertex flag equal to visit 1. Again I'll come back. I will check all the ones in the row 0 1 1, that is 1 2 1 1 0 1 2 1 3 1 4 1 5 6. I'll check all the values, and wherever there is 1, I will insert this vertex. If now we have 1 here, I will insert 2. If we have 1, I will insert 3 into q. You can see this. I have inserted into here 2 and 3. Okay, 2 and 3. Now that is only for those. So whenever there is a not equal to 0, that means there is a 1 in the matrix, and those arrays, those vertices are not visited, we are going to add into Q. Once after adding is over, what I will do? I will delete P equal to delete. Now when P equal to delete, now as already 1 is deleted here, 1 is deleted, and we what is the next element we have which is present in the queue? 2 and 3. Next element present is 2 and 3. Now I will remove 2, delete 2, print on the screen. Okay, see this, delete this one, and if it is not equal to 0, means if there is a vertex, I'll print on the screen. Then I'll come back again. While P not equal to 0, I will now check its neighbors. Its neighbors means what? 2's neighbors. Now whatever the numbers which are there in the row for 1, 4, 5, I will insert them in the queue. When I will insert? If they are not visited, but already 1 is visited, so I will insert only 4 and 5. Okay. Now check here, you come back here and again check if P I equal to not equal to 0, and if they are not visited, I will add. So only 4 and 5 are added, 1 is not added here. Okay. Once this is done, so by doing this, what we'll do? We'll remove all elements from the queue. We'll remove all elements from the queue, keep on checking and remove all the elements till it is empty. Once it is empty, by that time it is printed. Okay. Now check this here. If suppose at last, now what we are going to do, I equal to 1, I less than equal to n, I plus plus. I'm checking whether all the elements are visited. If not, we are going to print it. We are going to print DFS of that. Now this will never, if we remove these lines, this should work. But let me explain. If we have a disconnected graph, what are we going to do? In that case, some of the vertices are not visited. In that case, we have to come here. Or if the elements are not inserted in the queue, then you have to come back and check its neighbors. So this works when, this is when we have a tree and all. In a tree, if some of the edges are not visited, inserted, when we have to trace back, no, all. So when we trace back, that time this will work. Shall we run this program? Let me compile this one. Compile, run. Okay, it's not running. Build. It seems that file has not been built yet. Yes. Acha, parsing stage done. No to parse open pass project. Okay. I just installed, I think, editor. There is no compile, it seems. Okay, let me check what can be done. Close this one. Code block default has changed. Do you want to save it? Okay, save it. Save it. I can minimize this one. Okay. Now we have downloaded code block. What is the size here? View details. 148. Fine. This one will run. We have to install, I think, this one. WinGW. Okay. Do you what do you use? Which editor you use in your computer? Do you all use code block or Linux or TC? Am I audible? Participants. Participants. Yes. 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 Thank you. You all are there, no? Otherwise, I am doing program and okay. Now this is breadth first search where we are using Q. Now can you do DFS on your own? Can you do DFS? You have to use stack. I will explain the logic again. How you can go through all those. I'll give you time. Okay. Meantime, what we'll do, we will explore some of the other things like what, like Moodle. Moodle. On the Moodle, we will see what are some other things which are needed. Like now, tell me how many of you have submitted all these assignments, practicals? Are you facing any problem? Okay. Is everyone has submitted? Has everyone submitted your assignments? Let me check in DS Lab. DS Lab. Okay. So it's visible now to you all. See this, we have completed all these programs. Searching is over, sorting is over, almost 19 programs are over. Okay. And if you exclude these C programs, 5 programs, still there are 14 programs. Okay. So stack implementation, queue implementation, linear queue, circular queue, and I have not taken here the priority queue that is left here. Then single linked list, double linked list, stack implementation with C list, queue implementation with single linked list, linear search, binary search, bubble sort, selection sort, insertion sort, quick sort, merge sort. Okay. Again, sorting is left here, like heap sort and radix sort is not there here. So those things are not here. Then we have hashing program, that is not there. Hashing is not there. Radix sort and heap sort, 3 programs plus what? Plus what we left here, one more thing no here, uh, yeah, those 3 programs are not there. Okay. Then we'll have this one, BFS and DFS, these 2 programs. Now do you want to add me those heap sort, radix sort and hashing in your program list, practical list? 19 programs are, these are. Okay. Anyway, I will add those programs in the here in PVL. Okay, and explain those programs also. So what you have to do? I will explain those programs, write the programs, show you the code. You can implement and submit your programs. But as far as exam is concerned, I will ask in the A division and B division what they have done. So only those many programs you will take for the exam. And if there are any other programs which we have not taken and they have taken, then I will tell you. Uh, I will explain those programs also, so that it will be common for exams. Okay. Maybe code block is installed. Let me check. Code block is. Do you want to run code block now? Okay. Run this. Finish. Is the screen visible? Okay. So desktop, we have code block somewhere here, no? This one code block. Let me run this. Okay. Another program is unloading. Okay, fine. Do you want to start the program? No. In your configure search path GNCC compiler. So Control O, desktop. Okay, graph. BFS. No, it is. Okay. Running startup script, find the file broken. Okay. Now what we have to do? We have to find code block. So there is a problem with code block. It's compiler. We have to insert that code block compiler. No, what are the steps? I also don't use much this code block. Okay, so code block, it says native parser. Now loading. Do you know, has anyone faced the same problem? Okay, chart box. Okay, where is chart box? Okay, what it says? Upadhyay. Okay, fine. No, we have to insert. Where is that? It says tools. How to insert the code block? Compile in the code block? Any idea? Okay, let me check. Running script. Script plugin register. Edit startup subscript registers. Okay, let me compile this one. What is the error it gives? Okay, how to insert compiler into code blocks? How to add compiler into code blocks? Fine. Okay, what to do? We have to go to menu compiler, select a compiler, GNGC compiler, select tab. Then where it will be there? Installing supported compiler code block. Okay. Compiler, neutral setups, tabs, windows, open, setups given. Acha, open bin. This is for Linux. Okay. For Windows, we have to go to settings menu compiler. Settings menu compiler and GNGC select tab. Okay. Settings compiler. Okay. Then GNGC compiler. Okay, you have to include, I think, these things. So where is GNU compilers compiler linkers, search custom results copy. Okay, compiler settings. Then G++. Okay, we set all these things. Do we have C compiler? This will work, I think. 90 GNU C++ languages. Okay, this one. Follow G++, ISO C++, GNU C++. Okay, we'll include all. Let me see what will happen. Okay, only one. It will take only one. It's okay. What about debugging? Debugging, optimize debugging executable. Symbols. This one. Okay, then warnings. Enable all warnings. Fine. Anything else? Optimization O1, O2, O1 is enough. Okay, let me see this whether it works. Can't find compiler executable in your configured search path for GNC compiler. Path, maybe environment here, you have to set the path. Path also. Settings. How to set path. Can't find compiler executable in your configured. Okay. Has anyone has faced this problem in your computer? Can't find executable. Okay. This is, no, I have done this one earlier. I can't find compile executable from search path. Windows 10 it is. So what is the path here? Windows 10. Okay. Mine shows fine. gcc.exe. Just open settings compiler and click reset defaults and it will start working. Settings compiler and click restart. Let me check settings. Settings compiler. Default. Where is the default? Set default is not there. This set to defaults. Yes. Settings. Yes. Okay. Auto detected insertion path. This is compiler. C program code block. Okay. Auto detected. Is it detected? Okay. Let me check. Can't find compiler. Okay, error queue undeclared. It's working, I think. Okay, error queue undeclared first. Where is queue? Line number 9. Line number 9. Okay, let me close this program and run it again. Close file. Okay. Open again. BFS. Error queue undeclared first use. Q front plus plus. Where is Acha? Q is not. Okay, Q is not declared. Okay, let me declare Q of 20. Okay, no target, no errors. Run the program. Okay, so it's running. Is it visible? Is it visible to you? Yes, someone can answer. Are you there, all participants? Okay, okay, it's visible. Now let me take the same input. Let me take the same input in the graph which is given. So have you written down those values? This is, we have this thing. So what are those values we have? So this is 6 by 6 matrix. Then we will give some vertex and check. Okay. Maybe let me write these same values. Okay, we'll try the same one. Run. How many vertices there? 6. Now you have to enter. See this. Enter 1 if 1 has a node with 1. If vertex 1 to 1 has a edge, has a node with 1. So this is not node, it is the actual edge. If 1 has a edge with 1, else 0. So do we have loops? No, no. So it is 0. Next check, enter 1 if vertex 1 has a edge with 2. Okay, we'll change this one. We'll change what? We will change the printf statement here. Okay, we will change the printf statement, code block. Okay, enter what? Enter 1 if vertex percentage d has a edge with vertex d. Okay, save this, compile and run again. Now how many vertices? 6. If enter 1 if a vertex 1 has a edge with vertex 1, else 0. So there is no edge, so insert. Otherwise what you can take? You can take all the values in matrix form itself. Now check after 6 in this is one whole row, 0 1 1 0 0 0. Then the second row is what? If enter 1 if vertex 2 has edge with vertex 1, else 0. Now second row is 1 second row is 1 0 0 1 1 0. What is third row? 1 0 0 0 0 1. Fourth row is 0 1 0 0 0. Fourth row 0 0. Fifth row is 0 1 0 0 0 0, and sixth row is 0 0 1 0 0 0. So this is the matrix. Is it visible to you? The adjacency matrix is this. No, this is not. This is font. I cannot change. I should have changed it. So this is the adjacency matrix. Now enter the source vertex. If suppose if I enter 1, now this is how it is done. 1 2 3 4 5 6. That is the BFS traversal. You come here. You come to this and check here. If my source vertex is 1, it is 1 2 3 4 5 6. Suppose I change my source vertex now. Source vertex to say 6. Then what will be the values? Check here. If it is 6, do you want to continue the same input? Yes. I'll say yes. Enter the source vertex. I'll say 6. Now what is the value here? 6 3 1 2 4 5. Okay. Check here. 6 3 1 2 4 5. 6 3 1 2 4. Come back here and 5. Okay. Now suppose if I give say 4, do you want to continue? I'll say yes here again, and my source vertex now is say I'll enter 4. Now what are the value here? 4 2 1, as it is breadth first search. Okay, 4 2 1, then come back and 5. 4 2 1 5, then come back. These all are visited. Go to 3 and 6. You can see this. 4 2 1 5 3 6. Okay. Now has anyone written the, have you noted down any of the graphs for input? You can tell me the values. We will enter some input. Have you understood the program? Have you understood the program? What you have to do? Take the salting vertex, put into Q, then remove Q element from the Q if it is not empty. Check all its neighbors whether they are, if there is edge. If they are neighbors adjacent, insert them into Q. Okay. And when you remove from the Q, you print them. Then you go to next element, remove element from the Q, print it on the screen, check its neighbors. Okay. If they are not visited, if they are adjacent, put them into Q. So you have to keep on doing this till Q is not empty. Once Q is empty means what? The meaning is all are printed. All are printed. If at all, now we have to check a graph where if it is disconnected, what we will do? Suppose I will enter again. Do you want to continue? No, I will say no. We will exit here. Do you want to continue here? No. Okay. Let me run the program again. Let me run the program again. I'll run this one. Run. The number of vertex is 3. Okay. Now 1 to, there is a edge between 1 to 1. No loops. Yes, 1 to 2 there is a loop edge. 1 to 3 there is edge. No. What about 2? 2 to 1 there is a edge. As 1 to 2 there is edge. 2 to 1 is edge. 2 to 0. 2 to 2 is a loop. No. 2 to 0. No. Then what about 3? 3 to 1 and 3 to 2 there is no. There are no edges. You can see this. What is this meaning here? This means we have a graph. What is the graph here? See, graph is this one. 1 1 2 and 3. Is it visible? And we have edge 1 to 2 and 2 to 1, but 3 is isolated. 3 is isolated. So this is the one here. And if I give now you can see this, both are visible. Both the input graph is visible and you have a matrix is visible. Okay. Then now enter, if I enter say source as 1. So what is this we have? 1 to 2 I have BFS, breadth first search. What about 3? Actually 3 is 3 is not available, but as this is there are two graphs, we can print a message saying that graph is disconnected. So once we can print 1 2 and later we can print 3, but 1 2 3 it is not possible to connect to reach. In that case, if you don't want that, what we have to do, we can okay, now we have to see whether in the basics of graph, whether if it is disconnected for given vertex v 1 to 2, 3 is not possible to reach. In that case, you can comment this, the last line in the main. In the last line main, we have these 3 lines, no? Not in the main, it is in BFS. Okay, you comment this, and this will, that will not print that met the isolated vertexes. Now run this again. Do we have this one? Okay, do you want to continue? No. Enter. I'll run this again now. Compile and run. I'll enter the same input, 3 vertexes. Okay, 1 2 3. So 3 vertices, fine. So no loop, 0, 1 to 2 there is a edge, 1 to 3 there is no edge. What about 2? 2 to 1 there is edge, 2 to 2 there is no loop, 2 to 0 no, and 3 it is isolated, 0 0 0. Now suppose if I enter 1, see this, 1 to 2 there is a BFS, breadth first search. So 3 will not print as 3 is isolated. Do you want to continue? I'll say yes. And now I will give vertex source as 3. Now you can see only 3 is printed. 1 2 are not connected, you cannot print them. Okay, now we'll try the other one also. Yes, enter. Now source vertex will make it as 2. Now 2 to 1 is possible connection, 2 to 3 is not possible. Do you want to continue? No. Okay, have you understood the program? Any questions? Now I explained the graph with this, maybe in last 2-3 lectures I explained it regularly, at least 2 to 3 times. Okay, we have taken the example also. Now I will upload this program. I'll upload this program for your reference on the Moodle. Okay, you can refer this, and you try to run this program for all the inputs. You first draw the graph, enter proper graph inputs, run the program, and when you upload this program, you should also upload the output, whatever the output you have given, input has given, and what is the DFS, sorry, not DFS, BFS, breadth first search traversal. Okay, now what we have printed here, we haven't printed them properly. Let me print it. Okay, when I enter 3 and say 1 2, enter the vertex 0 1 0 1 0 0 0 0 0. I'll say starting vertex is 1, enter the source vertex 1. Now it is just printing 1 1 2. I don't want to print this. I should print saying that where I'm printing here. No, I'm printing print p. Okay, once you enter the source, enter source value, we will print when you call this one, we should print a message saying BFS. So BFS here, the BFS is maybe here. Before enter the source vertex, after that I'll print a message saying what the BFS is, printf print f new line. Okay, BFS breadth first search, breadth first search, or BFS traversal for given graph starting with percentage d vertex is and I'll print. Okay, this is enough. Okay, this is enough. Now check. I'll run the program again. Okay, what is there is error? Where is the error? Okay, semicolon. We need semicolon at the end. Okay, So I'll say 3, same thing. 1 to 1, no. 1, 0, 1, 0, 0, 0, 0, 0. If I enter, say, starting vertex 1, it says breadth first search BFS traversal for given graph starting with, okay, percentage vertex is 1, 2. Okay, no. Now what change you have to make? You have to make change here. As I am printing percentage D, I'll say comma. So what is source? Yes. Then I'll print a new line. Maybe that is good. That is okay. That will take something. Okay. Run it again. Run. 3 vertices. Uh, there is no loop. 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0. Okay. I'll print 1. It says breadth first search BFS traversal for given graph starting with 1. Starting with vertex 1 vertex is 1 2. Do you want to continue? If I say yes, now what is the next vertex? 3. Vertex 3, 3 vertex is 3. Do you want to continue? No. Okay, so this is working. Okay, with vertex 3, I will say vertex 3 here, vertex percentage D. Understood? So because of code block was not there, so we wasted some time. Okay, any questions for this BFS? Okay. Now what I will do, I have written a program for DFS also, but it was combined program. Now, okay. Can you try DFS on your own? Can you do DFS depth first search? I'll explain the logic. Okay, let me then take that program also. I'll just explain the logic. Okay, then we have to run the program. So we have that program BFS2. Okay, so this is both BFS and DFS here. Okay, now how the logic? Okay, so let me change something here then. File save as, save file as DFS, DFS 3.c. Okay. So in DFS, what we do? We use queues, no? So we use queue. So sorry, in BFS depth first search we use queue. Depth first search we use stack. So we don't need queue. Remove this queue. Then we need top, as it is we are using the stack. Remove front and rear. We don't need. Then we need matrix to store. We need stack. Fine. Then delete and delete not needed, add not needed, and BFS function not needed. So we have DFS push and pop. Okay. Now we'll remove those. So we'll remove BFS. BFS is removed. Add and remove. Add delete queue element. Okay, removed. Now what we have? DFS. Okay, DFS. Okay, now read the input, enter, read the input, then the adjacency matrix is that. Okay, fine. So we'll not use all that. We'll use, okay, we'll use only this one. Enter your choice. Source vertex, no. Enter source vertex, then we'll remove all this, choice and all. DFS. Do you want to continue? Okay, fine. While c equal to this, fine. Now, when you call DFS, what you do? We are sending as it is for DFS depth first search. Okay, let me save this file. Let me save and see whether it works or we have to make changes. Okay, it is working. I'll say enter the number of vertices again. Which loop you have to take? We'll take. Okay, we have that graph, no, with us. We'll take the same graph. We'll take the same graph. Okay. Now this is the program. Okay. Now, what is the depth first search for this same 1, 2, 3, 4, 5, 6? Okay. We'll take this one. We'll take input, enter the input, and we will try. Enter the number of vertices. What are the vertices? 6, 1, 1 has 1. Okay, we'll change that line. So it is 0, 1, 1, then 0, 0, 0. Second row is 1, 0, 0, 1, 1, 0. Third row is 1, 0, 0, 0, 0, 1. Fourth row is 0, 1, 1, 2, 3, 4 zeros. Then 0, 1, 1, 2, 3, 4. Fifth row. Sixth row is what? 0, 0, 1, 0, 0, 0. This is sixth. This one is sixth row. This one was the sixth row. Okay. Now check. This is the matrix I entered. I entered this matrix. Okay. Let me check. Okay. So this matrix I entered here. This one. This matrix is here. Okay. It's the same matrix here. The adjacency matrix is same thing. Now suppose my I want to start depth first search from this index 1. Depth is what? You come to 1, you either visit 2 or 3. You visit 2 or 3. If I visit 2, I will visit one of its neighbor adjacent node, either 4 or 5. Only one, not all. So I keep on doing this till the depth comes. Then I'll come back and I'll visit the other vertices. Suppose if I enter the source vertex has 1. Source vertex has 1. So what has happened here? Do you want to continue? What is the depth first search here? 136254. 136254. DFS. DFS is 135, 135, 6, 2 and 4. How it is done? You can see this. You can see this one. Either you can visit 2 or 3, only one. So it has taken 1, 3, then 6. So we have reached to the depth. Then you come back. You go to 135. Okay, 135 it is. Let me check what is the values. Sorry, 136254 it is. 136 136 136254. 136254. Okay. So 136. You come back, visit 2, then 5. Remaining is 4. So you will reach all the elements till we come to the depth, and then we'll take it again. Maybe I'll draw it again. We'll draw it again late. Wait. So this is the graph. The graph is 1, 2, 3, 1, 2, 3, 4, 5, and 6. Okay. Now suppose my starting index starting vertex is 1. Okay. Then how we will traverse? Either you have to choose any of the neighbors. Either you can choose 2 or 3, doesn't matter, because weights are not given. Once you choose 3, you come to its next one of its node which is adjacent to that. Okay, so we have only 6, no other loops. So we print 1, then 3, then 6. Now, are there any other nodes which are not visited and visited? No, there is no adjacent nodes here. And so what you have to do? You have to backtrack. You have to backtrack here. Now what about 3? There are no nodes which are there with the adjacent nodes with the 3. We have 1 and 6 which are already visited. So we will come back here. We will come back. Now check here. For 1, there are 2 adjacent nodes, 2 and 3, but 3 is already taken. So 2 is left. We will come here and we will insert into stack. So 2 is printed. Okay. Now for 2, you check all its adjacent nodes. So 1 is already taken. So either we go to 4 or we go to 5. Okay. So suppose if you go to 4, what you will do? You will print 4 here. You will print 4. This is anyway it is printed. Now 4. Do we have any nodes adjacent to 4? Only 2, which is printed. You come back to 2. Now for 2 you check what are adjacent nodes. We have 1, 4, 5. But 1 and 4 already printed. So you go to 5 and print 5. 136245 or 136, as you can take 245 or 254, doesn't matter. Okay. So what is it taken here? 136254. Now you can see one thing here. It is in our program we have considered the right side always. So it is 136, then 2 right side first and 4. That is we have considered 5 and 4. You can take any of the nodes, adjacent nodes. Now you want me to explain this in with using stacks? We have done this earlier. I will upload this program also. I'll upload this program also. Now you have to trace these both the programs. How this works? Let me explain that. Okay. Do you want to continue here? Okay. Maybe we will take one more vertex. Suppose if I take 4, if I take 4 as a, now see this, we'll take one more example. Suppose if I take 4 as the starting index, 4 as the starting index, then which are its neighbors? Its neighbor, 4's neighbor is who we have only one neighbor, 2. When you come to 2, either you can take 2 to 5 or 2 to 1, whichever path. Suppose if you take 2 to 1, okay, then what you will do? For 1 to 6, you print this, and you come back here, and later you print 5. Otherwise, you print 4 2 first, then print 5, come back here, then print 1 3 6 and all. Okay, let me run this program, run the program, and you will understand this one. Okay, do you want to continue with the same input? Okay, I will say yes. Now what is the starting index? I will enter 4. Now what output I am getting here? 4 2 5 1 3 6. 4 to 5 1 3 6. Let me write 4 2 5 1 3 6. Okay, 4 2 5 1 3 6. So how it is done? Initially this is the starting index, it is printed here. Now what is the next index attached to this? 2, that is printed. Now after this is taken, it has taken 5, so 5 is printed. Now are there any other nodes attached to 5? No nodes. So backtrack. Now 2, check if 2 has any other vertices adjacent to it. Yes, 4 is printed, 5 is printed. Now go to 1. Go to 1, print it 1. Now go to 3, go to 6, print 3 6. Come back here, check all the nodes again. Okay, understood? Now with stack, how we are going to do this? Let me take that also. Okay, we'll remove this one. We'll remove and draw it again and take a stack and understand this one. So this is 5 and this is 6. So this is the graph, no? 1, 2, 3, 4, 5, 6. Okay. Now suppose I'll explain this with this. If suppose 1 is the starting vertex, then how we are going to do this one? Take, oh my god, everything is cleaned. I think everything is cleaned. Okay, okay, fine. Draw it again. 1 2 3 4 5 1 2 3 4 5 and 6. Now 1 2 3 4 5 6. 1 2 3 4 5 6. 1 2 2 3 1 2 2 3 all zeros. What about 2? 2 to 1 4 5. 2 to 1 4, 5 other zeros. What about 3? 3 to 1, 6. 3 to 1, 1 and 6. What about 4? Only 4 to 2. 4 to 2 other zeros. What about 5? 5 to 2. 5 to 2 other zeros. What about 6? 6 to 3. 6 to 3 other zeros. So this is our adjacency matrix. Now how you are going to do this? Suppose this is my starting. This is depth first search. DFS traversal. Okay. DFS traversal. Here we use stack as a data structure. So we use stack as a data structure to store the values. So what you will do initially? So this is my stack. This is my stack. I will take the first vertex which I am visiting. In our case, it is 1. This one, 1. I insert 1 here. I insert 1 and I will pop 1 and I will print it. Print. I will print. I will insert 1 as well. I will print on the output. I will not pop. Okay. I will not pop. Let me wait. We will take this proper here. Okay. So this is my stack. Okay. And this is the output. What I will do? I will insert 1. Also, I will print on the output 1. Okay, this one. As it is depth first. Then what I will do later? I will either take 2 or 3. I will either take 2 or 3. Okay. Suppose if I take say 3. If I take 3, then I will insert 3 here and print on the screen. Print on the screen. Now 1 is already visited. Okay. 3 is visited. Now check 3's neighbors. We have only one neighbor, 6. I'll make it as visited. Push on the stack and print on the output. Print on the output. Now check. Do we have any other vertices attached to 6 which are not visited? No. 3 is there, but 3 is already visited. So just pop this one. Pop 6. Pop 6. Take it out. Okay. Now what is the status here? We have only 1 and 3 left in the stack. Okay. Now come back here. Backtrack. Check 1. 1. 3 is visited. So 1 we have one more node adjacent to 1, which is 2. Now which is not visited. Insert 2. Insert 2. Now 6 is not there. We'll insert 2. This is the status now. This is the status of queue here. 2, 3, 1. And you print on the screen. Print on the screen. Now check whether what are this is visited now. What are nodes attached next to 2? So we have 4 and 5. If you take 5, then you make it push it on this vertices and print on the screen. Now check for 5. There are no vertices which are not visited. 2 is already visited. You come back here. Now for check 2, whether any other vertex or vertices which are not visited and not printed. So 4 is there. You come to 4, insert into the queue. Okay, and print on the screen. Print on the screen. Now we are here. You backtrack. Check 2. Come to 2. See whether they are. You pop it and check its neighbors. All the neighbors are visited. You come here. You pop this. So pop 4. Then pop 5, pop 2, pop 3, pop 1. So by doing all this, what you get if once the stack is empty, by that time you are printed the result. Okay, you have printed the result. Let me check the program. So at what time it is? Time 1:15. So what input we had given for 1? It is 136,254. Okay. So this 136,254, 136,254. Okay. Now it is done. DFS. Now this is the same program. Once you read all the matrix, what you are doing, you are saying adjacency matrix is take the input, paint its adjacency matrix. Then for I equal to 1, then make all nodes, all vertices as visited I equal to 0. So none of them is visited now. Initially it is initially no vertex is visited, so make it 0. Then enter the source vertex. Ask source vertex from the user. Then call DFS source vertex and number of vertices. Okay. Then you come to DFS. Then you check if there are temporary variables ik. Push the starting vertex into stack. Then make that vertex as visited equal to 1. Then you pop the same, pop the first one, and check if it is 0. That means it is empty. But in our case, it is there. Some one vertex is there initially. You print that vertex. Which is 1. Now check while k not equal to 0. Check all the vertices which are neighbor to it. Neighbor, not all. Okay, now check here. For k not equal to 0, for I equal to 1, less than equal to 1, I plus plus, you check if a of ki not equal to 0 and visited I equal to 0, you push one of the element, then make it visited 1. Okay, and whatever you push, you pop that one. You pop that. Now, if k not equal to 0, okay, print that number and you take this. So this is the logic which is differing. When we have used BFS, it was queue. When you use the DFS, it is stack, and you can see this what we are pushing and popping. Okay, so there when you delete element, it is neighbor of the starting index, but here it is adjacent vertex of the given vertex. Okay, whatever we have pushed it, that element we are popping. So whatever we are where we are doing here, we are pushing it and popping the same element, checking its neighbors. Okay, and this one we don't need this. Okay, we don't need this, but this I'll put it into what has happened. I have to enter something, no? Maybe some break is put here. Undo, Control Z. Okay, where was it? Here. Okay, so you can put here comments. We don't need this, but it will be there in program. You check it later. Later you should tell me why it was there earlier. Huh? So push and pop. These are simple instructions of stack. So we are using stack here initially. Top to -1. Listed if we are using array. Stack, I am using stack. Okay. So both the programs I'll upload. Go through those programs. You should be able to type both the programs, write these programs on your own without needing any help. Suppose if your exams face to face, then in practical in our lab you will come and you will execute these programs. Meantime, for thermocline internal, it will be online. Any questions? Understood? Have understood this program? BFS and AFS. So next lecture I will start with trees basic, and 1 or 2 programs on trees. So so these both the programs will be there for your practical terms. Practical in the practical experiment list, both BFS traversal and DFS depth first traversal will be there in your program list, experiment list. Any questions regarding PBL? Are you working on it? I will share, maybe I will share the report today, but you complete the coding, properly, give the comment lines in your programs and make sure your program is working. And in the WhatsApp group, those whose PBL project is working, you give me a message saying yours is working. Maybe I will give you time. You can give me the program, then I will run it. Then in a group, we are going to present or give. You are going to give me a demo of that project. Okay. So today I will close here. Stop sharing. Stop sharing here. Okay, and end the meeting.